In the previous class, we discussed about DSP system and sampling process and discrete time sequences, and also DFT and FFT and its relationship between DFT and frequency response. Okay, we already discussed this one also, and this one is very important. The fast Fourier transform. Okay, what are the different types of the fast Fourier transform? What is the use of this one? Okay, and this table is very important. Please go through this table. Okay, and for that here this table will give how many number of the multiplies required for the DFT computation and how many number of the multiplies are required for FFT based computation. Okay, please go through this. These are the equations. For DFT, n square, number of the multiplications, and for FFT, n divided by 2 log of n with base 2 multiplications are required. Okay, please go through this. And linear time invariant system. Okay, in linear time invariant system, yeah, first here we discuss about what is the linear system. Okay, a system which the superposition theorem can be applied is known as linear system. Okay, then what is meant by the time invariant system? A system that is described by the same input output relation at all times is called a time invariant system. Okay, then what about the LTI system? LTI means a system that is both a linear as well as a time invariant. Then we call it as a linear time invariant system or LTI system. Yeah, these LTI systems can be represented in the time domain using linear constant coefficient difference equation. LTI systems in time domain can be represented using a difference equation. Okay, a unit samples or impulse response is used to characterize an LTI system. Okay, here the time domain convolution can be used to determine the response of an LTI system. Okay, which one will use time domain convolution that can be used to determine the response of an LTI system in time domain. In the frequency domain, the system transfer function is used to represent a system. Okay, here they given about the convolution. Here we know we are already familiar with this equation, convolution. Okay, here convolution is an operation that relates the input output of an LTI system to its unit impulse response. Here h of n is unit impulse response. X of n minus m is circular shift of the input. Okay, this is about the convolution. Here we can analyze the time domain approach of the LTI system. Okay, using Z transform, we represent the frequency response. Here, this is the equation for Z transform. X of e raised to j theta is equal to summation of n equal to 0 to n minus 1, 0 to n minus 1, x of n e raised to minus j n theta. Here you can substitute z is equal to e raised to j theta. Then x of z is equal to what? Summation of n equal to 0 to n minus 1, x of n z raised to minus n. Okay, then here system transfer function. What is the system function? That is the ratio of y of z divided by x of z. X of z is equal to y of z divided by x of z. That is the system function. We also call it as h of z. When we did inverse transform of this h of z, we will get the unit function. Okay. Next one is most important topic is decimation and interpolation in this. What is meant by the decimation and interpolation? The decimation and interpolation both are the DSP operations. Both are the DSP operations which can vary the sampling rate of a sequence. Which can vary the sampling rate of a sequence. Yeah, decimation is used to decrease sampling rate. Decimation is used to decrease sampling rate, and interpolation is used to increase the sampling rate. Okay, then the decimation, in this decimation process, we can drop some samples without violating the sampling theorem. What is sampling theorem here? Fx is equal to 2fm. You can allow the signal, okay, for the sampling in the frequency of the input signal below fs divided by. Okay, so the decimation involves dropping samples. Here we can drop some samples. That is the decimation. Interpolation means involves inserting samples with appropriate consideration to the samples around the point of insertion. In the interpolation, we can add some samples, inserting samples with appropriate consideration without violating the sampling theorem. Here in decimation, we can drop some samples. Okay, here just go through this. This is the block diagram of decimation process. What will happen here? Here, before decimating that means decreasing the sampling rate, what we can do here? We can decrease the number of samples. See here, x of n is the input. We given it to the digital low pass filter. Okay, the output of the low pass filter is W of n. Then we send it to the down sampler. We send it to the down sampler. Here, this down sampler, which can drop the some samples from the x of n. Okay, go here. The factor by which the signal is decimated. The factor by which the signal is decimated is called decimated factor. That means that indicates that decimated factor indicates how many number of the samples can be dropped from the input. Okay, here we know that the relationship between input and output relation for the decimation is y of m is equal to w of m of m, capital M, is equal to summation of k equal to minus infinity to infinity bk x of m into m minus k. Bk x of m into m, capital M, minus k. Wait a minute. Okay, so here y of m is equal to w of m, that is equal to k equal to minus infinity to infinity summation bk x of m into m minus k. This bk is the coefficients. Bk is the coefficients. Here, what is w of n? Here, w of n is equal to summation of k equal to minus infinity to infinity bk x of n minus k. This is the output of low pass filter. See here, output of the low pass filter. Okay, this is the case in which the sampling rate of x of n is divided by m to obtain the sampling rate for y of m. Okay, to prevent sampling theorem violation, the signal is first band limited using the filter with bk coefficients. To prevent sampling theorem violation, what we can do here? We can pass the input signals to the digital low pass filter. Okay, here the equation 2 allows computation of all samples. However, equation 1 specifies computation of only those samples that need to be kept. That is, every mth sample. Every mth sample, that means m. Mth means Here it's a decimated factor. Okay, mth sample. This is about the decimation process. Briefly explain the decimation process with block diagram. That is this block diagram, this which consists of digital low pass filter and downsampling. Just reverse of this one is interpolation. Here the sampler, up the sampler will come. Here the filter will come. Okay. Here interpolation, the input output relation for the interpolation, where the sampling rate is increased by a factor L. L minus 1 number of the samples can be inserted to the x of n. Say L is given as, here this is the output relationship, k equal to minus infinity bk w of m minus k, w of m minus k, where w of m is equal to x of m divided by L. Okay, remaining values are 0. This is the x of m divided by L means when m is equal to 0 as the input, as your input, then plus or minus L means it's a value of L here. How many number? This means interpolated factor. We'll discuss problem, then you will get it. Okay. The process of interpolation as implemented by above equation, these equations, okay, which requires first generating the sequence W of m. It requires the generating the sequence W of m by inserting L minus 1 zeros, and then applying the filter with decay coefficient. This is the block diagram. Upsampler, digital low pass filter. Here in first step only the frequency is increased by L times, but here in last step the sampling rate is decreased. In first step here is same, when the output of the W of m, the frequency is same. At the last step here, when we send the these values W of n to the downsampler, then some samples can be dropped here. But here initially, okay, when we send it to the upsampler, we can increase the sampling rate. Okay, to avoid the violation of the sampling theorem, we send it to the digital low pass filter. Okay, this is about the interpolation process. Okay, both are very important. Please practice it. Go through the decimation process and interpolation process. Both are the DSP operations. Interpolation can be used to increase the sampling rate, and decimation is used to decrease the sampling rate. Okay, just remember that. We'll discuss this problem here, then we'll get it. Here we have x of n is equal to 0, 3, 6, 9 and 12. Be interpolated using L equal to 3. Okay, see here, this is x of n, okay, L value is 3. Here we can insert how many zeros? L minus 1 zeros. Here can insert the L minus 1 zeros. What is the value of L minus 1? It's 2, right? 2 zeros are inserted in between the numbers. See here, let x of n is equal to this one and L value equal to 3. Now the W of m, the output of the upsampler becomes, the initial value is same. Initial value is same. Now insert 2 zeros. Then you can take 3 here, this 3. Then insert 2 zeros. Take this 6, insert 2 zeros. Take this 9, insert 2 zeros. And last 12, keep as it is. After 12, don't add the zeros. Okay, here we can use the low pass filter. Its coefficients are 1 divided by 3, 2 divided by 3, 1, 2 divided by 3, and 1 divided by 3. Here you can consider this is x of n. Here the bk. Here the middle one is 0, right? This is 0th position. This is 1 position. This is 2nd position. This one is -1 and -2. B of 0, B of 1, P of 2, B of minus 1, B of minus 2. So just remember these positions, coefficients. W of n as it is 0 to 12, like using this, like this we return this. Then we call the equation y of m is equal to k to the minus infinity to infinity bk x of n minus k. Here the limits for the k is from minus 2 to 2, minus 2 to 2. Then you can write here y of m is equal to minus 2, b of minus 2, w of m plus 2 in this equation. You can consider this equation. Expand the summation. Here we'll get like this equation finally. Then we substitute m value, k value here substitute. We got this equation. Now we substitute m equal to 0. Here see here w of 3. So 1 divided by 3 w of 2 plus 2 divided by 3 w of 1 plus 1 w of 0 plus 2 divided by 3 w of minus 1 plus 1 divided by 3 w of minus 2. Here the value will start from 0th position. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 0th position, right? See, what is the value of w of 2? 0, 1, 2. It's 0 only. W of 1 is also 0. W of 0 is also 0. W of minus 1 is also 0. And W of minus 2 is also 0. The value is 0. Similarly, y of 1 is equal to W3, W of 3 plus 2 divided by 3, W of 2 plus W of 1 plus 2 divided by 3, W of 0 plus 1 divided by 3, W of minus 1. W of minus 1 value is 0. W of 0 value is also 0, 0. Then W of 1 is also 0. W of 2 is also 0. What is the value of W of 3? W of 3 value is 3. Substitute here 3. 1 divided by 3 into 3, that is equal to 1. Like that, we can substitute up to how many times? 12 means here m value is how many values of m, W of m here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That means here 0 to 12. That means m value will vary from 0 to 12. Here up to 12 we have taken. Then here y of m is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. This problem is very important. Please practice it. This one. Okay, these are the important questions. Decimation and the interpolation process and problems on interpolation. Okay, please practice it. The next topic is FIR filter design and IR filter design. Okay, please go through this IR filter design. Here the IR filter design is, there are two types. Okay, one is unlock filter design technique, one more is direct design. In unlock filter design, okay, here first we do the unlock filter design, then we convert it to digital filter. Okay, here digital IR filters are designed using techniques that are based on unlock filter design method. There are different types of the unlock filter design techniques here: Butterworth filter, Chebyshev-1 filter design, Chebyshev-2 filter design, and elliptic filter design. Okay, so what we'll do in the unlock filter design? In this approach consists of designing an unlock filter to satisfy the filter specifications, okay, and then converting it to the equivalent digital filter using an appropriate transformation. You can transform the unlock filter design prototype to digital filter by substituting some values there, test values. Okay. Filter specification consists of passband ripple, stopband attenuation, and the transition width, and also it consists of stopband frequency, passband frequency. Okay, please go through this. What are the methods we are using? Okay, for IR filter design. Two methods: unlock filter design techniques and direct design. In unlock filter design techniques, Here we have some unlocked design filter design techniques methods. Okay, then after designing, we convert it to digital filter design by substituting by taking some transformation. Okay, go through this Butterworth full low pass filter program. It's also very important. Okay, just remember these are the important commands here. Butter, this is for frequency Z. You are already familiar with subplot and all. Okay, here the subplot for magnitude. To get the magnitude, we use the command absolute ABS. To get the phase, we use the command angle. Okay, and also here calculating group delay also. Okay, please go through this also. Sorry, yeah, repeated, right? I think. Yes, okay, same thing repeated. Okay, this one. Now the direct IR filter design. The direct IR filter design methods are based on the least square fit to a desired frequency response. Okay, these methods allow arbitrary frequency response specifications. Okay, here one such method is called as UOC design, which is available in the MATLAB program. Please practice this program. Okay, just go to the command here, UOC here, then for frequency, and remaining for the absolute plots and okay. Okay, please go through this. Please practice this algorithms. Okay, I mean MATLAB program. Yeah, one more is once they ask the question, Moss-McLellan FI filter design. This is a computer method for design of FI filters. It is based on one is image exchange algorithm and one more is Chebyshev approximation theory. The image exchange algorithm and one more is Chebyshev approximation theory. Here, which involves minimization of the maximum error between actual and desired frequency response. These techniques are not Parks-McLellan FI filter design. These techniques involve the minimization of the maximum error between actual and desired frequency response. Okay, it allows arbitrary frequency response specifications and designs an equiripple FIR filter. The equiripple means there we have these are called as equiripples, like okay, these up and low, up and low. These are the equal number of the up and low. It's called as equiripple FI filter. Okay, this is the program. Please practice it. This is the command. Okay, remade. This is for frequency. This is output here. So frequency response, ABS, and this is. Please go through this. It's also very important. Then here about infinite impulse response filter. The general difference equation for an LTI system defines an infinite impulse response filter. The corresponding transfer function for this filter can be shown in here. H of z, which consists of this is the y of z divided by x of z. Okay, these are the poles. Sorry, that means here the IR filter which depends on both inputs and outputs, previous outputs. Okay, see here, since an IR filter feedback in its structure, its stability depends upon the number and the values of coefficients. In general, an IR filter has non-linear phase response and does not provide constant group delay. Okay, we already discussed about what is meant by the group delay. Okay, here this is the differentiation of h of e raised to j theta with respect to e raised to j theta. It's called as group delay. Okay, here that group delay is not constant, not provide a constant group delay. Okay, the advantage of an IF filter is its smaller number of coefficients to realize a desired frequency response relative to an FIF filter. Here we use smaller number of the coefficients. Okay, fewer coefficients require shorter computation time, providing capability to handle a larger bandwidth for a signal processing. Okay, please go through this problem here. Yfn is equal to 0.9 Yfn minus 1 plus 0.1 x of n. Find the x of n. Okay, do the z transform of this one, then convert it to z of z is equal to y of z divided by x of z. Simplify this one. Okay, then here we'll get the frequency response of the IF filter. I mean this difference equation. This is the block diagram of this one. Okay, and magnitude response and phase response of this IFN. Let's go through this. Here, finite impulse response. Here, what is meant by the finite impulse response? Here, it depends on only the present inputs. Depends on only inputs. There is no feedback. That means it will not dependent on the present or previous outputs. Okay, the unit sample response of the FI filter lasts for a finite time dependent on the number of filter coefficients represented by bk. It is for this reason that such a filter is called as FI finite. Why it's called finite? The unit sample response of the FI filter lasts for a finite time dependent on the number of filter coefficients. That's why we call it as finite. Okay, this is the frequency response. H of e raised to j theta is equal to summation of k equal to 0 to L bk e raised to minus j k theta. Okay, then h of z, convert this one to h of z here. This is the h of z is equal to k equal to 0 to L bk z raised to minus k. Okay, here we discussed about the advantages and disadvantages. A FIR has no feedback in its structure. It is always a stable filter. There is no feedback. A symmetric coefficient FIR filter provides linear phase or constant group delay. This property makes this filter suitable for application that cannot tolerate phase distortion. This is the advantages of FIR filter. Then what about the disadvantages? The disadvantage of a FIR filter is that to obtain any desired frequency response, the number of coefficients is generally quite large. If the number of coefficients are more, then the computation time becomes large. Here, the larger number of coefficients require larger computation time. Okay, one problem here we'll discuss that is very important. Okay, this problem, this one only. Okay, here they given Yfn is equal to 1 divided by 16, Yfn minus 2 plus x of n. Sorry, actually it's IF filter, not FI filter, because here the Yfn depends on inputs and output also. Okay, just change it here. That's they given it's IF filter, FI filter. It's IF filter. Okay, then y of z is equal to 1 divided by 16, z raised to minus 2, y of z plus x of z. So here this is h of z. That is equal to z square divided by z square minus 1 divided by 16. Here I'll turn this one h of z divided by z here, then z divided by z plus 1 divided by 4 multiplied with z minus 1 divided by 4. That means this one is in the form of a square minus b square form. that is equal to a plus b, a minus b. Same thing here. Okay, using the partial fraction, we return this one. Then h of z becomes 1 divided by 2, z divided by z minus of minus 1 divided by 4 plus 1 divided by 2, z divided by z minus 1 divided by 4. Then h of n is equal to this one. Okay, and this one is FIR filter. This one is FIR filter design. Here y of z is equal to 0.5 x of n plus 0.5 x of n minus 1. Okay, this problem very important. Okay, then take the z transform of this one, then y of z divided by x of z, that means h of z, 0.5 plus 0.5, that is minus. Then take the inverse z transform of this one, h of z will get h of n is equal to 0.5 delta of n plus 0.5 delta of n minus 1. Then we know that h of e raised to j theta, that is the frequency response. Okay, here we have two coefficients, 0.5 and 0.5. That's why k equal to 0 to 1, bk e raised to minus jk theta. Okay, after substituting b0 and b1, that is equal to 0.5, we'll get this one. After simplifying this one, we'll write this one in this form. H of e raised to j theta is equal to e raised to minus j theta divided by 2 cos of theta divided by 2. This is very important. We can convert it to in this form. Okay, then e of e raised to j theta is equal to e raised to minus j theta divided by 2 cos theta divided by 2. This is equal to 0.5 plus 0.5 e raised to minus j theta. See here. Okay, convert this one in this form. Both are equal. Then I have written this. Here we can write this one e raised to minus j theta divided by 2. That is equal to e raised to j theta minus j theta is equal to cos theta minus j sin theta. In that form we return this one, cos of theta divided by 2 minus j of sin theta divided by 2. But this one is multiplied with cos theta divided by 2. Then here cos square theta divided by 2 minus j of sin theta divided by 2 cos of theta divided by 2. Then find the, this is in the complex variable, complex number. This is imaginary, this is, sorry, real part, this one is imaginary part. Okay, then here the magnitude is square root of this value and this value, add. Then here we'll get the magnitude is cos of theta divided by 2, cos of theta divided by 2. Then you can find the phase theta, phase response, that is P of theta, that is equal to tan inverse of, this is minus, what is the value here, imaginary, minus sin theta divided by 2, cos of theta divided by 2, divided by cos square theta divided by 2. Then tan inverse of minus tan theta divided by 2, tan and tan inverse, that is equal to minus theta divided by, this is the phase response. Then find the group delay. What is group delay? Differentiation of h of e raised to j theta with respect to e raised to j theta. Here, if you taken this one, this becomes complex. That's why I have taken this one. Okay. Then differentiation of this one with respect to e raised to j theta, that is equal to 0.5. Here the group delay is 0.5. Okay. In the next class we will discuss the numbering systems. Okay, floating point numbers, fractional numbers. Okay, in the next class we will discuss about that. This completes first chapter in the module 1. Okay, please revise or please go through this one. Okay, it's very important.